Welcome back. Today we're going to look at QuickSort. That was named as one of the most important algorithms of the 20th century and is widely used for system sorts and many other applications. Last lecture we looked at merge sort, another classic sorting algorithm that's used in many systems, and today we're going to look at QuickSort, which is used in many others. You can even get a QuickSort t-shirt nowadays. So what is the QuickSort method? It's also a recursive method, but the basic idea behind QuickSort is that it does the recursion after it does the work, whereas merge sort did it before it did the work. So the idea is first randomly shuffle the array. That's an important step that we'll talk about later. And then partition the array. So that's to divide it so that for some value j, the entry a of j is in place in the array. There's no larger entry to the left of j and no smaller entry to the right of j. Once we have the array partitioned in that way, shown here in the middle, right here we have k in its position, and we have everybody to the left, there's nobody greater than k, and everybody to the right, there's nobody less. Once we have it arranged in that way, then we recursively sort the two parts, sort the left part, sort the right part, and then after those two things are done, the whole thing is sorted. This method was invented in 1961 by Tony Hoare, who won the Turing Award in 1980 for this and other work. So let's look at a demo of how QuickSort partitioning works. The idea is to arbitrarily choose the first element to be the partitioning element. Since we shuffled the array, that's a random element from the array. And then we're going to maintain an I pointer that moves from left to right and a J pointer that moves from right to left. Let's look how it works in the demo. So we start again by picking k as the partitioning element. And then our method is to move the I pointer from left to right as long as what we have is less than the partitioning element, and move the J pointer from right to left as long as it points to an item that's greater than the partitioning element. So in this example, the I pointer stops right away because it's pointing to an R, which is bigger than the partitioning element. The J pointer decrements until it gets to the C, which stops there because that's less than the partitioning element. And so now what's going to happen is those two elements are out of place. The partitioning element's in between them and they're in the wrong order. So all we want to do is exchange those and then move on. Now we increment I as long as it's pointing to an element that's less than the partitioning element. Stop here at T because that's bigger. And now we decrement J as long as it's pointing to something that's bigger than the partitioning element. Stop here at I because that's less. Again, T and I are in the wrong places. If we exchange them, we'll maintain the invariant that everything to the left of I is less than the partitioning element, or nothing to the left of I is greater than the partitioning element, and nothing to the right of J is less than the partitioning element. So exchange them, increment I as long as it's less, stop at L. Decrement J as long as it's greater, stop at E. Those two elements are out of position, so exchange them. Now increment I, stop at the L, which is greater than K. Decrement J, stop at the E, which is less than K. And now at this point, the partitioning process is complete because the pointers have crossed and we've looked at everything in the array. In fact, J points to the rightmost element in the left subfile. That's everything that's not greater than K, so we can just exchange J with our partitioning element, and now we've achieved the goal of partitioning the array so that A of J is in its position, nobody to the left is greater, nobody to the right is less. Now the code for partitioning is straightforward to implement. Down below shows the state of the array before partitioning, during, and after partitioning. So in the end, the J pointer is pointing to the partitioning element V, which was in position V in the first place. All during the partitioning process, the code is maintaining this invariant where everything to the left of I is less than or equal to V, everything to the right of J is greater or equal to V, and we haven't looked at things in between. So incrementing I as long as it's less is a simple while loop, and then we put a test to make sure we don't run off the right end of the array. And decrementing j as long as it's pointing to a bigger element is similarly just a while loop where we put in a test to make sure we don't run off the left end of the array. Then there's a test to see if the pointers cross, swap the elements at I and j. When we get to the pointers cross, we break out of the loop and exchange the partitioning element into position. So that's a quick implementation of the QuickSort partitioning method. Now, QuickSort itself then is going to be a recursive program that uses that partitioning method. The first thing we do is the public sort method that takes the array of comparable items as its argument is going to do a shuffle, and that shuffle is needed to make sure that we can guarantee that the performance is going to be good. And then it calls the recursive method that takes as arguments the limits of the subarray that's going to be sorted. So then partitioning simply does the partitioning, tells us which element is in position, and then recursively sorts the left part, that's low to j minus 1, and then the right part, that's j plus 1 to high. That's a complete implementation of QuickSort. Again, as with merge sort, studying the recursive trace is instructive, and this one is kind of upside down as compared to merge sort. The first line shows the partitioning, where k is put into position. Then the method calls the sort for the left subfile first, and then that's going to be partitioned on this E, and so forth. And eventually we get down to small subfiles. Actually, our code doesn't do anything at all for subarrays of size 1, so we just leave those in gray. And then it does the right subfile and so forth. Again, studying this, a trace like this gives a good feeling for exactly what's going on in the recursive program. Let's look at an animation of QuickSort in operation. There's the partition. Now it's working on the left. Now it's partitioning the right. Now it's working on the left part of the right. Now it's partitioning what's left, doing the left part of that. And working from left to right by dividing each subarray in half as it goes. So let's consider some of the details in the implementation of partitioning with QuickSort. So first thing is it partitions in place. You could use an extra array and the partitioning code would be a little bit easier, but one of the big advantages of QuickSort over merge sort is that it doesn't take any extra space. It gets the sort done in place. Now, you have to be a little bit careful with terminating the loop. When we give you working code, it's not hard to see why it works, and you might go through the exercise of trying to implement QuickSort without looking at our code. And you'll find that testing when the pointers cross can be a little bit tricky, particularly in the presence of duplicate keys. Also staying in bounds. Actually, in our implementation, the test of the J pointer running off the left end is redundant. Why is it redundant? Well, the partitioning element's sitting there and it'll stop when it hits the partitioning element. But the other test is not in our implementation. And one key thing is that the way that these implementations work, if the file is, the array is randomly ordered, then the two subarrays after partitioning will also be randomly ordered. Actually, some implementations of QuickSort out in the wild don't have this property, and they suffer a little bit in performance. That random shuffle at the beginning is important and needed for guaranteeing performance. And the other thing I've referred to but not talked about in detail is the presence of equal keys. You might think it would be better to handle equal keys in some special way, and we'll talk about that in a second. But this general purpose implementation stops the pointers on keys equal to the partitioning item's key, and we'll take a look at why that's important in a minute. So now let's look at the running time estimates about why we care about QuickSort versus merge sort. This is extending the table we looked at last time. And you can see over in the right column here, QuickSort is quite a bit faster than merge sort. And again, a good algorithm is much better than having a supercomputer. Even on your PC, you can sort a huge array of 1 million items in less than a second and 1 billion items in only a few minutes. So again, this sort of timing is why QuickSort is so widely used, because it's simply just faster than merge sort. Well, in the best case, QuickSort will divide everything exactly in half, and that makes it kind of like merge sort. It's about n log n. And in the worst case, if the random shuffle winds up putting the items exactly in order, then partitioning doesn't really do anything except find the smallest, peel off the smallest item, kind of discover that everything to the right is greater. That's a bad case, but if we shuffled randomly, it's extremely unlikely to happen. The most interesting thing about the study of QuickSort is the average case analysis. This is a somewhat detailed mathematical derivation, but it's worthwhile going through the steps to really get a feeling for why it is that QuickSort is quick. So what we do is, as we did for merge sort, is write down a mathematical recurrence relation that corresponds to what the program does. In the case of QuickSort, the number of comparisons taken to sort n items is n plus 1 for the partitioning, plus what happens next depends on what the partitioning element was. If the partitioning element is k, any particular value happens with probability 1 over n. And if it's k, then the left subfile has k minus 1 items in it, and the right subfile has n minus k items in it. So for every value of k, if you add those up, the probability that the partitioning element is k plus the cost for the two subfiles, we get this equation. This looks like a fairly daunting equation, but actually it's not too difficult to solve. First thing we do is just multiply by n and collect terms. So NCN, n times n plus 1, and then these terms, every size appears twice, so it's twice the sum of from C0 to Cn minus 1. That's a simpler equation already. Now what we can do is get rid of that sum by subtracting the same equation for n minus 1. So NCN minus n minus 1 Cn minus 1, and then n times n plus 1 minus n minus 1 times n is just 2n, and then the sum collapses, just leaving the last term. This sum minus the same sum for n minus 1 just leaves the 2Cn minus 1. Now that's looking like a much simpler equation. Rearrange the terms. So we get n plus 1 Cn minus 1, and then divide by n times n plus 1. That's a kind of a magic step, but we'll see that makes it possible to solve the equation easily. Because that equation with Cn over n plus 1 equals Cn minus 1 over n is an equation that telescopes. The first term at the right is the same as the term on the left, so we can apply the same equation. So it's 2 over n plus 1. We apply for n minus 1. We get 1 less here, and we throw out a 2 over n. And continue that way, throwing out 2 over decreasing numbers all the way down until we get down to 2 elements, or C1, which is 0. Substitute the previous equation, telescope, and then that gives us an easy sum that we can approximate by an integral. It's 1 over x from 3 to n plus 1, and that's a pretty close approximation in this case. And that approximation gives us, it's about 2 n plus 1 natural log n comparisons for QuickSort, about 1.39 n log n. That's the average number of comparisons taken by QuickSort. And actually, for a random permutation of the input elements, which is what we do with the shuffle, the expected number of comparisons is concentrated around this value. It's very likely to be very near this value as n is large. So the worst case, QuickSort is quadratic. So complexity is going to tell us that it's a quadratic algorithm, if that's what its worst case is. But with the random shuffle, it's more likely that this lecture will end because of a lightning strike, or your computer will be struck by a lightning bolt. So we can discount that. The average case, which is extremely likely for any practical application, is going to be about 1.39 n log n. So that's more compares than merge sort uses, but QuickSort is much faster because it doesn't do much corresponding to each compare. It just does the compare and increment a pointer, whereas merge sort has to move the items into and out of the auxiliary array, which is more expensive. So the random shuffle is a key for good performance in QuickSort. It gives us the guarantee that the worst case is not going to happen, and also it allows us to develop a math model that we can go ahead and validate with experimentation. You run QuickSort and you count compares. If you did the random shuffle, it'll be about 1.39 n log n compares, and its running time will be proportional to n log n, and it'll be a fast sort, and that's what people do, and that's why people use it. Now there are some things that you have to watch out for with QuickSort because the implementation is a bit fragile and it's easy to make mistakes, and you'll find textbook implementations or implementations out on the web that wind up running in quadratic time in certain situations. You have to be a little bit careful of that. Even if everything is randomized, if there's lots of duplicates and the implementation's not done quite right, the QuickSort might take quadratic time. So let's summarize the properties of QuickSort. It's in place. It doesn't use any extra space. The depth of recursion, so that's again dependent on the random shuffling, is going to be logarithmic. You can limit the depth of recursion by always doing the smaller subarray before the larger subarray, but that's not really necessary nowadays as long as you've done the random shuffle. Oh, and by the way, QuickSort is not stable because partitioning does one of those long-range exchanges that might put a key with equal value over a key, another key with the same value. So it's a little more work to make QuickSort stable, maybe using extra space. So what about in practice, this is our fastest sorting algorithm, and there's a few ways to make it even faster. And we looked at some similar things with merge sort, and it's definitely worthwhile implementing for QuickSort. First thing is small subarrays. Even QuickSort has more overhead than you want for a tiny array like one of size 2 or 3 or 4. So you can implement it to cut off to insertion sort for small arrays. And the exact number that you use is not too critical. Anywhere between 10 and 20 will improve the running time by maybe 20%. Also, you could just not do anything for small arrays and then do the insertion sort in one pass at the end. So that's a first improvement. Second improvement is to try to estimate the partitioning element to be near the middle rather than just arbitrarily using the first element, which on average will be at the middle. So one thing that we can do is sample the items and then take a median of the sample. That's actually not worth the cost for large samples usually, but for 3 it's worthwhile. Slightly reduces the number of compares, increases the number of exchanges paradoxically because more exchanges are required when the partitioning is right in the middle. So that'll also improve the running time by maybe 10%. So this is a summary of the optimized QuickSort with cutoff to small subfiles and median of 3 partitioning. So partition usually happens pretty close to the middle when you do that sample and median of 3. And then small subfiles can just be left unsorted to be picked up with insertion sort right at the end. So this gives a feeling for the number of items that have to be touched during QuickSort and kind of an explanation for how it gets the sort done so quickly. That's a summary of QuickSort, our best sorting algorithm that we've seen to date. Now we'll look at a problem that's related to sorting called selection that's also well solved by QuickSort partitioning. This is a simpler problem. We're given an array of n items that are ordered, and our task is to find the kth largest. There's lots of important applications for this. So, like if we wanted to find the minimum item, that's k equals 0, or the maximum item, that's k equals n minus 1, or the median, that's k equals n over 2. And there's many kinds of applications when people processing data want to find the top k or the median or other order statistics. So that's what selection is all about. Now, here's an example where we want to use theory as a guide. What kind of efficiency might we expect in a selection algorithm? Well, first of all, it's easy to see that we can solve selection in n log n time. How would we do that? Well, we just sort the array, and then if we want to find the smallest, you look in the first position, or the largest, you look in the last position, or the median, you look in the middle. In fact, if k is small, the running time is going to be proportional to n. Because if you're looking for the smallest, you can just go through the array and find the smallest in one pass through. Or for 2, you find it in 2 passes through. So you can imagine trying to look for a selection algorithm that takes time proportional to n. And also the lower bound is n, because you have to look at everything. If you don't look at everything, you might miss the one item that you're looking for. So from these observations, it's clear that what we'd like is a selection algorithm that takes linear time. But at this point, the question is there a linear time algorithm that works for every k? Or possibly selection is as hard as sorting. This kind of question plagued a lot of people in the late 60s, early 70s as these types of problems emerged for computing applications. So it's an interesting question to think about for sure. Well, in his original paper in 1961, Hoare gave a solution to the selection problem based on partitioning. And the idea is just a version of QuickSort in a way. We're going to do our partitioning so that we get entry A of j in place in the array. Nobody to the left is larger, nobody to the right is bigger. But then when we're doing selection, what we'll do is just go in one subarray or the other, depending on where j is. If j is equal to k, we're done. We found the kth largest. If k is to the left of j, then we just do the left subfile. We just set high to j minus 1. And if k is to the right of j, we just do the right subfile, set low to j plus 1. And that's all this code does. You could do it with a recursive call, but this just does it by resetting the values of the parameters. Do one partition, then check whether your kth element is going to be in the left part or the right part. Reset low or high accordingly. If it's equal, then you found it and you return it and you keep going until you get to a point where you have only one element. That's a QuickSort like implementation solving the selection problem. Notice again that it depends on the random shuffle at the beginning. That's going to be important for performance. All right, so there needs to be a mathematical analysis to characterize the running time of this program. And the fact is that QuickSelect, this method, takes linear time on the average. We won't give the full proof. It's actually quite a bit more complicated than the one just done for QuickSort. But intuitively, we can see kind of what happens. Each partitioning step maybe splits the array approximately in half. So that means you'd have, if it did exactly in half, you'd have n plus n over 2 plus n over 4 and so forth, which adds up to about 2n compares, so linear cost. If you do it actually doesn't cut it in half exactly each time, only on average. So you need a fuller analysis like the one we did for QuickSort. And the bottom line of that analysis gives the number of comparisons required as a function of n and of k in terms of this formula here. And if you plug in k equals n over 2, you get the result that the number of compares required to find the median, and that's the highest value this formula can take, is 2 plus 2 natural log of 2. So linear time to find the kth largest for any value of k. Now again, it's going to use, this is a method that's linear time on the average. It's actually going to be quadratic in the worst case. But again, the chance that that'll happen with a random shuffle is less than the chance that we'll be struck by lightning. It's a probabilistic guaranteed fast algorithm. Now, from a theoretical standpoint, that's a little unsatisfied. And in 1973, there's a famous paper that found a compare-based selection algorithm that guarantees to solve the problem in linear time. This was a real landmark in the theory of algorithms because for a long time it was not known. We knew we could have the average case be linear time, but could we find a worst case? And this paper found such a construction. Now, in practice, this construction is rather high, so the method's not really used in practice, and so there is still the goal of a fast, guaranteed linear time selection algorithm that maybe somebody in this class will invent someday. This is another example where we use theory as a guide. It's still worthwhile to look for a practical linear time worst case algorithm. Maybe somebody in this class will invent that. But until something like that is discovered, use the quick select based on QuickSort partitioning, and you can get linear time selection when you don't need a full sort. That's selection, a simple problem like sorting that is well solved with QuickSort partitioning. Now we're going to take a look at what happens when we have significant numbers of duplicate keys, which is not at all unusual in practical applications. So in fact, often the purpose of a sort is to bring items with equal keys together. Like the example that I gave where we had cities and times. There's a lot of detailed data in the times, but maybe the whole goal of the sort is to group them by cities so we can ship out the data for each city to each city. And there's plenty of other examples like that in data processing where we find maybe remove duplicates from a mailing list or all the job applicants that we get, we might want to sort them by the college attended. So the sort, there's huge files with huge numbers of duplicate keys. So our sort, it's worthwhile to take a careful look at what the implication of that is. So again, typical characteristics, we have a huge file, but small number of different key values. So let's look at our algorithms in that situation. So merge sort, it doesn't matter that much what the key values are like. Actually, we can show that merge sort always uses between 1/2 n log n and n log n compares. QuickSort, actually they were, up until the 1990s, the most widely used implementation took quadratic time for files with large numbers of equal keys. And it was actually found by an applications user. And that's the standard QuickSort that was in all the textbooks, almost all the textbooks. If you did not stop the partitioning on equal keys, it would run in quadratic time. So we want to do better than this. So the mistake happens if we put all the items equal to the partitioning item on one side, which is a natural way to implement it. And the consequence is, if you have all the keys equal, then partitioning doesn't really do anything. It just peels off one key to do a file of size n, then you get a subfile of size n-1, and then n-2, and so forth. And the result is a quadratic time algorithm. Our implementation, we stop the partitioning scans on items equal to the partitioning item. And then in that case, when all the keys are equal, it's going to divide it exactly in the middle. And then in that case, you get n log n compares. But actually, when you think about it, why don't we just put all the items equal to the partitioning item in place? That's really a desirable way to look at it, and let's take a look at that option. So the goal is so-called three-way partitioning. So what we want to do is get the array into three parts, so that now we have two pointers into the middle, one that is the boundary between the keys that are less than the partitioning element and those that are equal to the partitioning element. Another one that's the boundary between the keys that are equal to the partitioning elements and the one that's greater, and then in the middle are all the equal keys. That's what we'd like to arrange. Now, until the 1990s, conventional wisdom among people implementing systems was that it wasn't worth doing this. But actually, it's a problem that Edgar Dijkstra had proposed in the 70s as an example of a programming problem. He was really interested in analyzing correctness of programs and showing that how you could convince yourself that this program was operating as expected. But in the 1990s, we figured out that really this was going to be an effective way to sort. And this was taking a look at the QuickSort that a user found was broken. And now this method is incorporated into plenty of system sorts. So let's take a look at how it works with the demo. It's more complicated than standard QuickSort partitioning. A bit more complicated because there's more to do. So now we have our I pointer, which is right to the left of stuff we haven't seen yet. And then we have two other pointers that maintain these boundaries. Everything to the right of GT is known to be greater than the partitioning element. Everything to the left of LT is known to be less, and between LT and I is known to be equal. And all the method does is maintain this invariant. So let's do an example or two and see how that works. So we increment I and then figure out what to do. So now it's less than the partitioning element. So what we want to do is increment LT. So now we have one that's definitely less than the partitioning element, and LT is pointing at the partitioning element. And so now increment both LT and I. So that's the first case there. So now we have a second item, B. That's less than the partitioning element. So we exchange it with LT and increment them both. So we're moving the smaller ones than the partitioning element to the left of LT and keeping LT pointing on the partitioning element. Now what about when we get one that's greater than the partitioning element? So in that case, we exchange the one over at the right with I and decrement GT. So now we have one over to the right that we know is greater than the partitioning element. Notice that we didn't increment I because that element Z that was over on the right really hasn't been compared with the partitioning element yet. But we did decrement GT, so we made progress. So now what happens here? Now I is pointing to a bigger one, so we're going to exchange it with the one at GT and decrement GT again. And again, Y is bigger, so exchange it and decrement GT. Now we have the C, that one's smaller, so that's the first case. So we'll move it to the left of LT and increment both LT and I. W's a bigger one, that has to go over to the right. Now we have I pointing to an element that's equal to the partitioning element. And what are we supposed to do then? Well, to maintain the invariant there, we just need to increment I. And again, it's pointing at one that's equal to the partitioning element, increment I. And now one more time, and now it's pointing to one that's greater. So we exchange that with GT and decrement GT, and I's pointing to the one that was there, and that one's smaller. So we exchange it with LT and increment both I and LT. And now we're at a point where the pointers have crossed, I and GT have crossed. There's nothing that we haven't examined yet. So our partitioning is complete. Here's a trace of Dijkstra three-way partitioning for his problem, which is when there's just three different values in the file. Our problem, we were treating partitioning equal to the partitioning element as one value, less than as another, and greater than as another. And so this trace illustrates how we always make some progress and eventually we get the file sorted. The implementation is amazingly simple. The whole partitioning process for three-way partitioning in the modern programming language like Java simply maintains the invariance as described in the demo. If we find one that's less, we exchange I and LT and increment them both. If it's greater, we exchange I and GT and decrement that. Otherwise, we increment I. Could hardly be simpler. In fact, is simpler in many ways than the standard implementation of QuickSort. In fact, there's an argument for just using this implementation of QuickSort and forgetting about HORS because it performs so well in so many practical situations. Here's a visual trace of three-way QuickSort for a situation with plenty of equal keys. And again, when there's lots of equal keys, then there's going to be a place where one of those is chosen as a partitioning element, and then a big chunk of the array gets handled just in the partitioning process. Now there's actually some deep reasons why this method is important. And one thing to do is to realize that the lower bound that we talked about before depended on the keys being distinct. The worst case for a lower bound is when the keys are all distinct. But if we have a situation where there are lots of equal keys, that model is wrong. It's not too difficult to get a similar lower bound for the model when we know that there are some equal keys. So, for example, this is a rather complicated formula, but not too bad. And it says that if you know that the ith key occurs xi times, you can write down a lower bound for the number of compares that are going to be required in the worst case. And what's interesting about three-way partitioning is that the number of compares that it uses is equal to this lower bound within a constant factor. So that's entropy optimal. What that means is whatever the distribution of equal keys in there, this thing is going to use a number of compares that's proportional to the best that you could possibly do. The proof of this fact is quite beyond the scope of this course, but it's still an important fact. And the bottom line is that if you randomize the order and use three-way partitioning, then there's a lot of applications where your sort routine is going to be linear, not n log n. So it'll be much faster than merge sort in other methods for really a broad class of applications. So taking a look at equal keys carefully is something that can lead us to very efficient QuickSort implementations. Now we'll take a look at how the sorting algorithms that we talked about are expressed in the systems that we use every day. Now, the key point is that sorting algorithms are essential in a very broad variety of applications. And all of us use sorting algorithms pretty much every day. Many obvious applications like organizing your music library or displaying your search results or listing feeds in your web browsers. There's some other applications that are not so obvious where we use sorting as to make a problem easy once you know that they're sorted. And so, for example, finding the median. If it's already sorted, then it's easy to find the median. And other statistical problems are like that, or finding duplicates. The problem of finding duplicates by itself is not quite obvious what to do, but one easy way to solve it is to just go ahead and sort. And then there are plenty of applications that we'll see later in this course, like data compression or computer graphics, like finding the convex hull, applications in science, such as computational biology, or in systems development, where having an efficient sort is absolutely crucial. So because there's all these applications, most programming systems have a fast sort as an important part of their infrastructure. And Java is no exception. So Java has a method called arrays.sort, and it's intended to be a general purpose sorting method for use by Java programmers. And now that you have some understanding of the classic methods, you can have a better idea of why arrays.sort is the way that it is. It has the infrastructure that allows it to be used for all types of data types and all types of ordering. So it's got a method that implements comparable, and then it's got a method that uses comparator, so that you can use the natural order, or you can provide a comparator and provide your own order for any type of data. It uses actually both QuickSort and merge sort. It uses a tuned QuickSort for primitive types of data and a tuned merge sort for objects. Why two different? It's just the designer's assessment of the idea that if a programmer is using objects, maybe space is not a critically important consideration. And so the extra space used by merge sort maybe is not a problem. And if the program is using primitive types, maybe performance is the most important thing, and so they'll use the QuickSort. To invoke arrays.sort, you have to import the namespace from Java util arrays, and then all you need to do is invoke arrays.sort. I just answered this question, why do we use different algorithms for the two types? And this is maybe arguable. Now, I referred to this idea of a good system sort. There was a good system sort that a lot of people used for many years. And in 1991, there were some scientists at Bell Labs that were using QSort for a scientific problem, and they were used to it taking just a few minutes, and then they realized that it was taking hours of CPU time. And the fact was that all the QSort implementations at that time in Unix had this flaw. Well, there were two flaws, and one of them is a little complicated about the way the array is ordered. The other one was for arrays that had lots of equal keys, and this Wilson-Becker problem had lots of equal keys. It was quadratic time. System designers, John Bentley was one of the designers who took a look at this problem, and that led ultimately to the development of the three-way QuickSort that we use today. He worked with Doug McElroy, and they wrote a paper that outlined this problem and talked about some of these things. And they had a three-way partitioning method that was somewhat like the Dijkstra method that we show, but a bit more complicated. Another thing they did was, rather than shuffling the array, they used what's called a method for choosing a partitioning element called Tukey's ninether. Tukey's a statistician, and he had this particular method for order statistics that has some interesting properties, and used that for the partitioning element. This paper was very influential, and that basic method is widely used. And Tukey's ninether is just pick 9 items out of the array and take the median of the medians, and that's the ninether. Very inexpensive, and they had macros to do this, so it used not too much cost to find a partitioning element that's much closer to the middle than if you used a random one. The reason they used it is they thought it got them closer to the middle, and they also don't like some system designers don't like the idea of using random choices in a system method because of the way that it changes the state of the system. So they felt that it got better partitioning than a random shuffle, and it was also less costly than generating random numbers, including this change of state problem. But there's a problem. So you would think that the system sort would be completely solid with all this research and all the development that's gone into it. And in fact, there's a file out there, and you can go to our book site and get it, that will actually break the Java system sort. There's a killer input that will make the thing run in quadratic time. Actually, it usually crashes because it's recursive and it crashes the system stack. And it can cause all sorts of problems. There's a killer input for the system sort. And it can be disastrous in various systems. And the reason is they didn't do the random shuffling. McElroy himself actually found this problem that you could, while the sort is running, figure out an input that would make it crash. And so you can just run that program. If the sort doesn't use randomness, then it's vulnerable to this attack. So which algorithm should we use to sort? That's really a key question. We've looked at a lot of sorting algorithms, and actually there's hundreds of sorting algorithms out there. We've chosen the most important and the most interesting for you, but you could literally spend a year reading all the papers on sorting. And they still continue to be invented. New algorithms are developed that are found to have good characteristics all the time. And really the key idea is really important to think about because it applies to all sorts of algorithmic problems. On our way, we've been talking about rules of the game. What is it that we care about in a sort? It's a little bit more complicated than just put stuff in order. There's a lot of attributes that different applications have. Like stability, that's a fairly sophisticated attribute that you really have to think about and maybe not be aware of. Maybe your computer is parallel. The sort has to be parallel. We found that equal keys make a huge difference. I didn't really think about that at the beginning, but it can make a huge difference. Maybe the way your computer's memory is organized make a difference. Maybe the keys are small and the items are large, or maybe the keys are really huge. Do we need guaranteed performance? Are we happy with random performance? Do we know, is the array randomly ordered? You can think of a matrix shown on the right here where we list out all the possible attributes, and then there's algorithms that work well for different combinations of attributes. But the thing is, there's way more possible combinations of attributes than there are algorithms. So there's going to be situations that are going to require an understanding of what it takes to engineer a sort method that's appropriate for your application. There can't be a system sort out there that's going to cover all possible combinations of attributes. Now, usually it's going to be good enough, but it's definitely worthwhile to understand what's going on with different sorting algorithms in order to even find improved performance over the system sort. So here's a summary of some of the things that we've talked about. We've talked about 6 different sorting algorithms, and we've talked about a bunch of attributes. For example, the top line, selection sort is in place. It always takes about n squared over 2 comparisons. And one of the things to remark about it is that it only uses n exchanges. And so forth. Insertion sort, best case linear, quadratic, in place and stable, and it'll work well if the file's small or partially ordered. Shell sort, we don't know. It's running time, it's not stable, but it's a fast method for intermediate size files and not much code. Merge sort, n log n guarantee and stable, but not in place. Need that auxiliary array. QuickSort, not stable. Quadratic time, worst case, but that's unlikely to occur if you do the random shuffling. And it's the fastest and most useful in practice, particularly if you make improvements to deal with duplicate keys. And it's interesting to note, we've looked at important and classic algorithms that are widely deployed, but we don't have a useful practical algorithms in wide use that's got all of these characteristics, that's in place and stable, worst case n log n. There's versions of merge sort that come close, but they're too complex for practitioners to have adopted them. Those are some of the situations that we encounter when developing a system sort, and QuickSort certainly plays a role in most system sorts.